everyone. Thank you so much for coming today, and we're excited to hear our speaker today. And sorry, I was making sure the recording was on. I'm Brielle, and I'm one of the organizers for this year's Quantitative Seminar series for the Converse Lab. And I'll begin by acknowledging the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. We also acknowledge that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. So I'm excited to introduce our speaker today, Michael Springborn. Michael is an environmental and resource economist and associate professor in the Department of Environmental Science and Policy at UC Davis. He completed his PhD in 2008 at the Donald Bren School of Environmental Science and Management at UC Santa Barbara, where he studied under the Economics and Environmental Science NSF training program. He works on problems of resource management and decision-making under environmental risk and uncertainty. He's interested in several applied areas, including disease, invasive species, endangered species, fisheries, and climate change. And he typically uses methods from econometrics and dynamic optimization. And in the chat, I will share his website and the Nature Policy Lab that he co-leads. And I'll also share the links to his slides for today. And for everyone joining us today, if there are any questions, or if there are any key important questions, we can take them during the talk. Otherwise, we can save them for the end. So thanks everyone for joining today, and you can take it away.
Great. Well, thanks, Brielle. I really appreciate the opportunity to be here, the invitation and the opportunity. Welcome to my pandemic bunker here. You can see my elliptical over one shoulder, maybe the whiteboard here to the right. So strange times, but really enjoy the opportunity to be here and hopefully have a conversation with you all, especially towards the end. What I'm going to present today is some joint work with a PhD student that I worked with here at UC Davis, who's now at Colgate University in the Department of Economics there, Pierce Donovan. So definitely a lot of credit for this work should be shared with him. And as Brielle mentioned, there are some links being shared for these slides. And on the second slide, you'll find links here to the Nature Policy Lab, which is a shared lab between myself, Jim Sankiriko, Matt Reimer, Mark Agerton, and some other natural resource environmental economists, as well as the students that we work with. So that'll take you to a page that looks like this, so you can kind of see some of the things that we're up to. And then another link here to my own website, where if you're curious about any of these papers or other papers that might come up, you can find them here on that publications tab. All right, but to jump into the topic of the day, what I'm going to present to you here is going to draw on a couple of papers that I worked with in collaboration with Pierce and some others. Mainly the second paper here, an effort to balance conservation and commerce. So a motivation for this work comes from this sense that a lot of the sort of models that economists and other natural resource managers work with in thinking about managing fisheries or other natural systems, historically, at least the versions that economists have worked with, have been fairly constrained in terms of the objectives that are considered. So often, we might be focused on maximizing some sort of profit that comes out of a given fishery. But we clearly have issues of certain species that become degraded and maybe threatened or endangered. Those species might overlap with species that we're looking to harvest. And so this creates this tension between trying to exploit the resources that are still relatively healthy and okay, reasonably okay to exploit, while also figuring out how to protect these other species from a conservation standpoint. But as you might imagine, that profit objective and that conservation objective, those take very different forms. And so the key motivation for this work is to try to figure out how do we bring these together in a rigorous way that helps us to identify if we've got some dynamics laid out for a system and mathematical equations that we think are reasonable, how do we use that framework not just to identify what would be the ideal actions to take with respect to, say, harvest or other decisions, but also then how do we implement that in a world where we don't just necessarily have regulators with magic fingers that can perfectly pull the strings in a system, but we rather have policy instruments like marine protected areas, or we've got maybe price instruments for pricing bycatch. And so what I'm going to show you today is a framework that we're developing, have developed, to identify that ideal sort of action to take, conditional on a given model of a system, and then also how you can translate that into a policy instrument to help make that happen in the real world. Okay, so to lay out the kind of problem that we're going to be concerned with, I'm going to use a metaphor first that has nothing to do with fisheries or conservation, but suppose you're kayaking on a river and you're a fellow like this, hoping to stay, hoping to stay upriver here and not pass a certain threshold and go over the waterfall. Going over the waterfall would be terrible. And if an economist asks you to value how bad that would be, you would say, I can't really answer that question. It's just absolutely horrendous to go over that unless you're a professional kayaker like this fellow here. So the idea is that you're trying to stay in a relatively safe zone, but the current is fickle. You don't have perfect control. Sometimes it is overwhelming and kind of takes you in a direction that you wouldn't necessarily not like to go, even if you're paddling with maximum effort. And a key here is that your long run survival is not guaranteed. And hopefully you can start to see how this metaphor starts to match up with some natural systems that we're concerned with. So what I'm going to develop here is what we're calling a shadow value viability approach that is meant to be applied to a system with these kinds of features. We've got some sort of threshold that we're concerned about crossing. And in the metaphor above, that was going over the waterfall and having a really bad experience on the rocks in the depths below. Or in the case of conservation is species extinction. That outcome can't be avoided with certainty. So we know in infinite time, if a population has some chance of going extinct in infinite time, it's basically guaranteed to go extinct. If you do cross the threshold, it results in disaster, extinction, or going over the waterfall. It is practically irreversible. For today's purposes, we'll think about, in the model I'll show you, it will be perfectly irreversible, but we could also apply this to a system where you might cross a threshold into a zone where recovery is possible, but maybe not for many, many decades. And finally, it generates damages that are essentially either difficult or almost impossible to value. So, you might think of yourself going over that waterfall. How much would you be willing to pay to not go over this 100-foot, 200-foot waterfall? Probably everything that you own, right? So this is not a really well-posed valuation question. There are just certain outcomes that economists should acknowledge are either very difficult or almost essentially impossible to value, right? Like how much would you be willing to pay to avoid certain death? Everything you own. In the conservation context of today, how much would we be willing to pay to conserve a particular species, to keep it from going extinct? That's such an extreme outcome that I'm not really sure that sort of willingness to pay question is really well posed. So we're going to try to convince you, or I'm going to try to convince you that this is a reasonably practical way forward in, despite not having that information, that extinction is massively costly. It's a huge loss of value, but it's a very difficult number to try to identify. So the example I'll focus on today is a fisheries example, but those kinds of general properties of this kind of problem, I think apply in lots of different contexts, whether it might be water quality, flood management, climate change, invasive species. And in fact, there's some interesting problems in space exploration where you're trying to land a Mars rover without crashing it into a rock and destroying the vehicle that actually mathematically share a lot of the similar properties, which is kind of an interesting application in this Oh No It All paper. current approaches for valuing degradation of a species, that is sort of a decline in the population of a species that might be threatened or endangered, I would argue are fairly unsatisfying. So if we've got population on the horizontal axis here, current approaches often involve some sort of assumption of a constant loss per unit as the population size declines. Or if you look at some valuation studies, they focus on discrete jumps from a species being non-listed to then being threatened to then being endangered, and trying to elicit individuals' willingness to pay to say reverse one of those steps. And I think that's useful information, it's valuable information, but it's not necessarily the kind of information that we need to drive a management model for decision making. What we'd really like to know as our population abundance changes is what the value loss is incrementally, and also not make an assumption that that's going to be constant over time. The application today will focus on leatherbacks, turtles, and arguably if we've got a relatively healthy population, the loss of one turtle, while terrible, is not as costly as the loss of an additional turtle if that population is in a much less healthy state, say near extinction. So there's some sense that there's going to be some curvature to the value of these species as that population declines. But a question is, what does that look like, and how do we operationalize that for decision making? I mentioned earlier that we've got a couple of different kinds of goals that can come up in natural resource management. Economists, for for obvious reasons, we tend to focus on maximizing the net revenues or net profit that might come out of a system. From more of a conservation perspective, we might care about a specific viability goal. That is, ensuring the avoidance of some threshold, let's say avoiding or staying above some minimum level of a population. That could be a quasi-extinction threshold, where below that the population is basically assured of going extinct, or you could set that to actually zero, which is actual extinction. The population is completely gone, but we're trying to avoid some bad threshold over some time window, capital T, so maybe that's 20 years or 30 years, with some confidence, which we will call delta here. So as I mentioned earlier, if there's some probability that a species goes extinct in any given year, you can't ever ensure with 100% certainty that the species will persist over an infinite time horizon. So that's why we're focusing on a finite time horizon and some sort of confidence that's not necessarily 100%, but that could be 99%, or that could be, say, 95%, or whatever you're trying to achieve. Okay, so then if we were to state that objective mathematically, or that constraint mathematically, that would be this: that a species or a system stays above that threshold, or the species is surviving, is not extinct, when the population at any given time tau is above, stays above that minimum threshold level, starting at time t and going up plus cap t period. So that might be 25 years into the future. So it's really these elements here, that threshold level, which we're going to just set to 0 for extinction, the time horizon that you're concerned about, and the confidence level. That's going to those terms are going to be sufficient for pinning down this viability goal. And it's this sort of goal that we're interested in trying to figure out, how do we bring this into the sorts of natural resource management models that we're used to working with. And of course, this is all going to be conditional on the starting state. So what does your population look like to start with, and what the stock dynamics are of that population, both from natural variability as well as any sort of anthropogenic pressure that might be brought to bear on that population. Okay, so as I mentioned before, a typical approach is for to model a manager concerned with maximizing the net present value of their actions, where the action is given by A. And we're going to make that here, what we're adding new to this problem is to make this conditional on that viability constraint that we just worked through. So this expression here for the present value of profit, if you're not familiar with it, just says we get a certain amount of profit in any given period, depending on the action we take and the population of the species that we're dealing with. And we're going to sum that up over time. And here we're able to do that over an infinite time horizon, but that is discounted. That's a pretty typical approach here. So this is our discount factor, beta. And so the manager's objective, which is a very standard natural resource management approach in bioeconomics, is to maximize these discounted long-run stream of net profits that come out of the system. And we're taking an expectation here to deal with the fact that there is some uncertainty in this system, so we don't know the future with certainty. And that uncertainty is going to enter the stock dynamics, what this population looks like in a future period. And I should mention here that we're going to be focused on the stock of leatherbacks, of these turtles, but the profit here is going to be coming from harvesting a different species, the swordfish species that actually provides the fishery revenues here. Okay. So one way to try to solve this problem, you could look at this and see we've got an infinite horizon here. That can be a bit of a challenge, but for many decades, folks employing bioeconomic modeling methods have taken models just like this and solved them using a Bellman equation form, and that's this expression here. What that does for us, if you're not familiar with this particular approach, is if we've got some sort of population here, we're interested in this function called the value function V that describes the expected net present value at any given population level you might be at, given that you're making optimal choices. Okay, so this tells you the present expected optimized value of being at any given point in this state space. And so this allows us to simplify the problem down to thinking about what action should we choose today to maximize not only our immediate reward, but what we can call a continuation value here. That is the value that's going to come from this system in the long run. So what that takes into account is that if you drive down whatever valuable population this is today, that there will be a loss in value. And if you allow that population to increase, there will be an increase in value. But it basically is a way to simplify this from being an infinite horizon problem that you've got to deal with to basically kind of a two-period style problem. But of course, the challenge is we don't know ahead of time what that value function looks like. And I'm not going to get into it today, but there are numerical techniques for solving for what that value function looks like value function iteration, which I'm happy to talk about later, but those are sort of standard methods. For now, you can just sort of hopefully trust me that we have, in a sort of a standard model like this, we have ways of uncovering this value function, which again, this is important intuition here, captures that expected net present value of being at any given level of this stock, say at X prime, and that allows us to understand what we're gaining or losing as we make choices that drive that stock either up or down. Because we're going to build off of this in order to fold in this conservation objective that I noticed, or that I discussed before. Okay, before I get to how we actually deal with this challenge of this viability goal, it bears kind of explaining why this is a hard problem, why this isn't something that's already been handled in the past with standard methods. So here's our viability goal again up here. And in simple terms, we're trying to keep our population X above some threshold over capital T periods with a confidence or a probability that is equal to or above delta here, equal to or above like 95% or 99% or whatever it might be. But note that this is what is called a joint chance constraint. It operates over capital T periods, and that could be 25 periods, 50 periods, 100 periods, whatever seems appropriate. So graphically, what that looks like is given by this blue zone here. So suppose I'm a decision maker and I'm thinking about managing my system and choosing an action at time 0. I want to make sure that this viability constraint, this viability goal, is met over cap T periods. But as we go forward in time, as we actually move forward in time, and we go from 2022 to now me being a manager making this decision in 2023, when I make that decision in 2023, I don't just care about the future up through this point, but now I care about the future up through cap T plus 1. So notice that my viability window here continually shifts forward in time as my decision period goes into the future, right? And why is that the case? Well, if that window didn't roll forward in time, so we use this metaphor of a rolling window, if it didn't roll forward in time, by the time my decision period sat in this point here, just before cap T, all I would care about would be the survivorship of the species over a single period, and I would allow a lot of degradation of that species to happen because I'm only concerned about conserving it over the last single period. But of course, that's not the intention here. If we care about, say, preserving these leatherbacks over the next 50 years, that's not a window that should shrink as we advance into the future. That's a window that should stay at 50 years, even as we move ourselves into 2030, 2040, 2050. We should always be concerned with preserving the species for some number of periods into the future. Okay, so that presents us with this rolling window style of problem. And when we've got this joint chance constraint that sits over multiple periods all at the same time, this makes this dynamic programming or Bellman equation form that I showed you a few slides back, it turns that into an intractable problem. It can no longer be solved just in a straightforward way with standard techniques, which is probably one reason why this hasn't really been treated up to this point in time. It's an unusual constraint in that it has to do with what happens jointly over these cap T periods, not necessarily what happens in any one individual period, because in this framework, a little bit of additional risk in one period is fine if you have a little bit of less risk in another period, but that's being considered jointly over cap T periods. So it's this awkward constraint that we have to deal with that blankets many periods at one time, which presents us a computational challenge. All right, so here's a return to this Bellman equation form that we introduced before. And up through this point, it's quite standard. And we can solve it, except we've got this joint chance constraint that implements our viability objective here that we need to figure out how to get past that. So how do we do this? We add this extra feature. So we add a constraint to this model where, if you recall before, I penciled out this value function. And actually, let me redo this drawing here to allow myself to go negative with the function. So we looked at this sort of cartoon drawing of a value function before, and now what we're doing is we're saying, if you get down to the threshold, we're going to posit that there's some very bad value that's associated with that. We don't know a priori how bad that is, but we're gonna say it's quite bad, and in fact, it's negative. And this could be in the millions or hundreds of millions or billions, but this is a very large, very bad value. And so what we end up doing is we say, yes, when we're at a relatively healthy population, we still derive a lot of value from the system. But if we allow it to approach this threshold, suppose that the threshold is a population of 0, that is extinction, that's going to be associated with a very bad outcome. What we're calling here some sort of extinction loss. And what we do is we actually solve this problem here where we impose the value at a population of 0. We impose that that has to be this negative omega value, and then we look over different levels of that negative omega value. We basically ratchet that value to a more and more extreme loss until we get a solution that satisfies this joint chance constraint. So essentially we pull this joint chance constraint out of the problem and sort of set it over here to the side in a second stage, and we can solve this tractable problem up here with this penalty for crossing the threshold, in this case, driving the species to extinction. And each time we just guess different values of omega, and we have more of a sophisticated algorithm to iterate over different values of this omega until we get a value that is just large enough to achieve our viability objective. Okay, so that's a quick, hopefully intuitive introduction to the basics of how we then turn that into a tractable problem. And then from that, our goal is to identify what is this policy function. That is, for any given level of the stock we care about, what's the ideal action to take? And that is going to be one that's going to maximize this long run stream of profits while at the same time ensuring that our viability objective is not violated. Okay, so this is going to get a little bit more into the technical weeds of dealing with value functions, but hopefully the intuitive, the quick, probably all too brief, but intuitive introduction of value functions will help you follow at least some of this intuition. And that is that we can actually start to, once we have introduced this penalty to the value function of allowing the system to hit this undesirable, disastrous outcome of extinction, we can then do some interesting and fun things with the value function that emerges from that, and that is decompose it into a couple pieces. One is this standard piece, and it was the way that I defined the value function earlier in this talk, that it's the expected present value of the stream of net profits. So that's still in there. But then a second piece that we have that we can split off is this expected present value of omega. And this is going to be a key piece that's going to feature throughout the rest of this talk and in the application. And that is when we impose, backing up here, when we impose this penalty for allowing the system to cross the threshold, that penalty will then propagate back out through the value function, because the value function embeds an understanding, or it embeds the sense that if you allow the population to degrade, you're going to get ever closer to this negative omega, very disastrous payoff, and that potential, the expected value of that potential, is then going to be incorporated into that value function. So we've got two things that we want here. We've got the net revenues from this fishery that we'd like to try to enjoy and maximize, while at the same time embedding all the way back out to healthy levels of this leatherback population the expected present value of that extinction loss that we don't, as I introduced in the very beginning, we don't really have a good handle on what in the real world, what the true omega would be, what all of us would value the extinction of loggerheads to be, or sorry, of leatherbacks to be. But what we're arguing here is we don't actually need that. If we have our viability objective, we can identify that capital omega that is sufficient to then drive the care and precaution that we need to avoid extinction with the confidence that we want to avoid it. and that then will drive this expected value of that potential loss. It'll embed that in the value function, and it'll be something that we can then incorporate and be incentivized by, no matter how healthy or degraded the turtle population might be. So here is that, what we call this shadow value function, which is given here in purple. Again, it hits negative omega by the time we get a population down to 0. But as I mentioned, the way that this works in a dynamic programming framework is that propagates out, and we can understand what that marginal shadow value is, i.e., what do we lose, what's lost if that population takes a marginal or an incremental step down, or a marginal incremental increase or improvement in its status. Okay, and the expression that we've laid out here is a new one here, but it just helps you to see that what this function represents is the notion that you could hit that very high loss, that negative, that impactful penalty, with some probability at some point in the future. That depends on the action you take and the stock of the species that you're managing, and that could hit at some future period in time. And we still have discounting at play here as well. So here, this function omega, little omega, is going to represent the discounted expected likelihood of actually feeling that penalty of the extinction loss. And I'm using this language of a shadow value, and loosely speaking, for us here, we call it a shadow value because it's not a value that we actually observe in the world, right? Like, it's not like an X vessel price for biomass of landed fish that we can observe at a port as those fish are sold from fishermen to, say, a processor. It's not an observed value like that, but it's actually this, what we call a shadow value, right? Not a value that's concretely observed, but rather emerges from the model. There's one other wrinkle that I need to mention, and that this, the viability objective that we laid out for ourselves is only achievable in some part of the state space that we call, that others before us have called the viability kernel, and we maintain that language. What that means is there could be areas like this kayaker finds himself here, or where an endangered species might find itself, where the population is so degraded that you cannot actually achieve the viability objective as stated. So essentially, we're solving this problem assuming that you're still, at least today, within that viability kernel. So that's just a technical detail that I need to mention, but we can kind of ignore that for the purposes of the rest of the talk. Okay, so now getting a bit more concretely to our specific application, we apply this shadow value viability approach to leatherback turtles in the context of those turtles being caught as bycatch in a swordfish fishery. And this swordfish fishery spans a lot of different regions. It includes coastal California and Hawaii and other regions. Of course, bycatch is a massive sustainability problem globally. This picture here is just a nice cartoon demonstrating the fact that shrimp harvest in certain places is very notorious for the unintended but not unexpected capture of other species, some of which could be threatened or endangered. But to go back to our leatherback turtle example, to just get a visual here of what that looks like on the California coast here in this map, historically, where swordfish were fished in this region before an MPA was put into place is given by some of these teal dots here that are sort of distributed up and down the coast. But in 2001, a marine protected area was put into place, which is given by this white boundary here, in order to protect the leatherback turtles in this system. And so you can see that after 2001, most of that fishing that fishing really declined, and what was left of it became centered in Southern California here. What's simultaneously layered over here is just one example of how, you know, it's not necessarily the case that this marine protected area is the one place where it's bad to fish because of turtle bycatch. And in fact, there are places over here that are worse to fish in white, as estimated by their model, that are outside of the marine protected area. And there are places within the marine protected area here in dark blue that are actually fairly good to fish. And when I say bad or good to fish, that's in terms of the potential for leatherback bycatch. So this marine protected area is a bit of a blunt instrument that it provides protection, but is arguably overly prescriptive or overly coarse. What we'd really like to do is try to figure out, how do we provide fishermen incentives to use information like this or other information that they have at hand to make smart choices about where to fish and how to avoid leatherbacks. That would involve not just spatial location, but gear choice, timing of day, maybe depth of the hooks, and so on, just a collection of different actions in order to avoid the leatherback. So one of the points that we're trying to make here is that there's a lot of opportunity to sort of change the way in which we protect these leatherbacks, to free up fishermen to exploit valuable resources like swordfish, while more efficiently achieving our viability goal as laid out before. Okay, so in this particular fishery, we've got the choice variable here being fishing effort in terms of vessel days in a season. So the higher A is, that's a greater number of days in the season where vessels are out fishing for swordfish, and they get revenue from that, as well as they face a cost that increases as they spend more days out fishing. And that fishing also leads to bycatch of these turtles that increases as A increases. So the larger the number of days, or the greater the number of days you spend fishing, the more bycatch that we're going to see in this model. Now, I should mention a very important simplification in this model, in this paper, is that we allow for just one margin for fishermen to adjust to control bycatch, and that's just here A, the number of days that fishermen are fishing. In the real world, there's going to be multiple margins for adjustment, as I mentioned before, like spatial choice, gear type, the way the gear is used. Here, we're going to set aside that complexity and just focus on that one margin for reducing bycatch. Okay, so we've got some fairly complex leatherback population dynamics given by this function G, and we don't really have time to go into the gory detail of that, but the simple version of it is laid out here. We've got recruitment of juveniles given by a Poisson process. Their survival to adulthood is given by a Bernoulli process. The mortality of adults is a negative binomial that's like a Poisson process, but allows for the variability to be not made to be equal to the mean, if you're familiar with the negative binomial. We've got bycatch mortality that we also model as a negative binomial. All that detail is not super critical, but it's just a way for us to achieve demographic stochasticity when this population, especially as the population goes to a smaller population level. And why that's important is when you have a small number of individuals, there's a lot more variability in the recruitment. For example, because it's harder for individuals to find each other to then reproduce. So we want to allow for that demographic stochasticity in order to have a more realistic small population dynamics, especially when we're concerned about species viability. All right, so as we go about solving this model, we've got a social planner to start with who is choosing swordfish effort in order to achieve what I mentioned before, maximizing the net present value of the revenues that it generates while maintaining the viability constraint. Then from there, we go on to then model a regulator who's either choosing a price instrument, a price per unit of bycatch, a price per turtle caught by these swordfish fishermen, or a quota on the allowable level of these turtles to be caught. So the regulator is now instead choosing an instrument because they can't directly control each fisherman's specific actions, but rather we're going to use a market-based instrument, either a price or a quota, to then in a decentralized system of fishermen produce the same or a very similar outcome as the one identified as ideal by the social planner. So that's the idea here. All right, so from this, we get a solution to what we call this policy function. That is, what is the optimal action to take in terms of fishing effort for swordfish, depending on what our leatherback abundance looks like at any given point in time. So if we've got a population here of leatherbacks, this would be the ideal level of fishing effort. We've got, in this particular example, a fairly low leatherback population. Okay, then we can identify this also at the same time, this value function that I described before, but then the fun exercise from there is to decompose that value function into the two pieces that I described before. So here's that net value function, the one that's going to actually drive decision making, but it's composed of a couple of things that we're hoping to capture. So one piece of it is this green line, and that is the value in the system from the profits, the net present expected value of the long run stream of fishery profits from swordfish. That's the thing we want to exploit and have the fishermen enjoy. But at the same time, in that value function, we have represented this shadow value. That is, what's the value? And you can see that this is actually negative. You know, what happens to value as this leatherback population declines and starts to head towards extinction? And you can see how this shadow value function pulls down the revenue only focused value function in a way that embeds or encodes or acknowledges the loss of value as a species might decline, or as a bycatch species declines to extinction. So it's a way of incorporating that into the value function. All right. So just stepping forward here to think a little bit more about how this policy function is actually derived. When we're dealing with a bycatch price, the profits in the fishery are given by the profits that we described before, but they actually incorporate this bycatch fee, this price that fishermen have to pay per unit of bycatch caught. And then alternatively, in a quota-based approach, the regulator just sets a quota of the number of turtles, the maximum number of turtles that can be caught in a season. And once that quota is reached, that's it. Then things shut down. So here's a view of what these policy instruments look like. So this is an example. This is obviously, this model sets aside some real world complexity for simplicity, but it's a way of starting to see concretely how a regulator could use this sort of framework to set policy. So along the horizontal axis here, we've got leatherback abundance. And one way to look at this, one approach to the policy would be to use a quota. That's in orange here. And that's the acceptable number of turtles caught as a function of the leatherback. So the more leatherbacks you have, if the population is relatively healthy, then that allowable quota, it could be fairly high. But as the number of leatherbacks declines, so does that quota down to 0. Similarly, if we've got a bycatch price here, when leatherbacks are relatively at a healthy population, that price per turtle can be relatively low, but it's going to increase as that leatherback population falls. And I see here that I'm sort of running out of time, so let me skip that final one in the interest of allowing for more questions. I can come back to it if we don't have too many questions, and just sort of from there summarize what's happening with this shadow value viability approach in a nutshell, what we're trying to achieve here is optimal population viability management. That involves, when we have these survivorship type constraints, this joint chance constraint that sits over many periods at a time, that turns standard approaches intractable. So we need a new approach or an extended approach. And that's what here we're calling this shadow value viability approach. And that allows us to come up with a rigorous valuation of how costly it is when there's marginal changes in the threatened population, even when we're far away from extinction. So if this is a potentially threatened species that we're concerned about, we get a sense of how even marginal changes in that relatively healthy population matter and how we can fold those in and value those in order to identify a management solution and then ultimately look to achieve that through instruments that can work in a decentralized world where we've got decentralized fishermen actually making the choices that matter for bycatch management. All right, so let me pause there, and I think we maybe have about 13 minutes or so for questions, and for that I will, I suppose, turn back to Brielle.
Awesome, thank you so much for your presentation. Yeah, so people, if you have any questions, put them in the questions box, or you can raise your hand, use that feature, and I can unmute you if you'd rather ask a question that way. Yeah, so thanks again for your presentation. I guess as we wait, I can ask a question myself. So I was wondering about the window size in this whole process. Like, how do you find that length, and does it have to be an equal length, or could you make it variable? Could it grow or shrink, and or is that not computationally efficient? Or I was just wondering about that.
Yeah, so that was a detail I glossed over, and you're savvy to press me on that point. So I think Brielle's asking about this cap T. So what is that time frame over which you're trying to achieve that viability constraint? So ensuring that these leatherbacks don't go extinct with 95% confidence over, say, cap T equals 30 years or 50 years. And the answer to that is this is still in the realm of a preference parameter that needs to be given by either stakeholders or regulators. And so we don't take a particular position on what that has to be. You know, I think you'll see these in degraded species plans, like threatened or endangered species plans, where if there is a concrete objective presented, often there'll be a time horizon that's mentioned. So there's nothing sacred to it being 25 years or 35 years and so on. And so that's really just something that we need to decide, either managers or policymakers, as a preference. As well, this delta. So what is that confidence with which we're trying to achieve this particular viability goal? And in the paper itself, you can check that out. There's a link there. There's a sensitivity analysis section that looks at, you know, what happens as we vary that time horizon, or what happens as we vary that confidence.
So does this approach require that time to be a specific interval, or can you have like, okay, one management scenario is going to be, or at least one little box, like do all those boxes have to be the same size? I guess that's what I was wondering. The blue boxes, like the length of them.
My safe answer is the boxes, yes, need to be the same size. And I think there's a reasonable argument for that to be the case, right? Like if we're concerned with keeping leatherbacks viable for the next 50 years in 2022, then that's probably the same time horizon we want to use once we get to 2023. If we decide at that point that going forward we want to change, and instead we want to actually think about viability over 75 years or 100 years, then we can make that change and implement that. But at any given point when you're solving the model, all of those T's, I think they need to be the same as you think about solving the model. but that doesn't mean you can't come back later and decide your cap T should be something different and then resolve it.
Okay, cool. So Dan Vondo has a question. So Dan asks, said, very interesting. How sensitive are the results of this model to the choice of acceptable probability of extinction? E.g., would the optimal policy look much different if someone had a tolerance for a 5% versus 8% chance of extinction?
Yeah. Okay. So that's given by this delta here. So I guess the difficult answer here is, we've got some results for that in the paper in this sensitivity analysis, but I would actually think that I think what you'd really like is a general answer, and unfortunately I think it's going to be system dependent, and part of the reason for that is tweaking that one parameter has a lot of different effects, or has multiple different effects. So one of the things it does is it shrinks the viability kernel. So that viability kernel is the state space for the range or the set of turtle population levels at which this viability goal is even feasible, right? So at a very low, almost extinct level of these turtles, you wouldn't be able to achieve this viability goal of, say, survivorship over the next 75 periods with 99.9% confidence, right? So as you drive up the level of that confidence, the set over which this constraint is feasible to implement shrinks. And then you're also trying to stay within that zone with greater confidence. So there's sort of multiple effects that it has. So of course that drives you to want to be in a safer part of the state space, i.e. maintain an even higher level of leatherback turtles. And what's actually kind of fascinating about that is one of the things that we found is you can actually end up in a place where you have higher fishery net present value when you apply that more stringent viability constraint, that more stringent delta, ensuring survivorship with a higher confidence. You can end up actually increasing the profits that come out of the system, because you're in a space now where you're not constraining the fishery as aggressively, because you've moved the whole system over to a higher level of turtles where that's where you have less danger of the turtles degrading. So once you get to that new place, it's actually a better place to be, but there is a costly period of transition in between where you'd really have to sacrifice in the short run in the fishery in order to get to that higher level of leatherback turtles. So changing delta actually leads to some interesting effects. But they're going to be specific, I think, to the biological and user elements of the system.
Cool, very interesting. So Adam Hayes has a kind of similar venue of question. So Adam, also, so you can see it yourself. Adam said, how sensitive is this model to values of omega? And is this model still useful for values that are not some arbitrary large negative value? There could be some species or maybe local extinctions that are less like to fall off a waterfall.
Yeah, let me try to find the right slide here to think about this. Here we go. Okay, so I believe, so we have two omegas running around in this model. One is capital omega, and I'm assuming that I think Adam is referring to this capital omega. So how sensitive is the model to the choice of that omega? One key clarification here is that the value of omega here is actually endogenous. It's determined within the model, not given by the modeler like us. What it is the minimum sufficient extinction loss. So it's the value of extinction loss that's just big enough to drive enough care and precaution, and in this case that means reduction in fishing effort. So capital omega is the extinction loss that's just big enough to drive enough of that care and precaution such that we meet this viability objective everywhere within that viability kernel. So omega actually emerges from the rest of the model, capital omega does, as opposed to being a value that we impose as a parameter. But and then to pick up on another element of Adam's question, a complexity that we glossed over was metapopulations, right? So there's a possibility of local extinctions, and we're seeing this on the California coast with certain species, with the marine heat wave and the loss of kelp, that we've got certain species that have gone extinct in certain zones but are still existent in other zones. That's definitely real world relevant. It's not an element of complexity that we dealt with here, and it would, in order to start to tackle that problem, we'd have to, I think, first start with, you know, how does our viability objective change when we're not talking about viability of one population, but rather a set of metapopulations, and that's really interesting. So I guess I would need input from others as to what we think we're actually, what we want to try to achieve in terms of a metapopulation viability objective, and then from there we could think about how, if and how this model could be adapted to deal with that. But I think that's a really interesting question.
Cool. So Mark Shrell has a question. Mark says, really interesting talk, Michael. I'm wondering if you or others have thought about this approach with respect to decentralized recovery or rehab efforts rather than harvest. For example, say population size is very close to or below some quasi-extinction threshold and no one wants it to fall any lower. Money is being spent on recovery projects that are distributed across space and time, but there is no central control over who does what and where. Presumably the price or quota is then based upon fish saved rather than fish caught.
Yeah, so I'm gonna step back here to the two papers that I mentioned. The turtle and the turtle bycatch as a function of swordfish harvest is in this paper here at the bottom. And if you have these slides, the papers are hyperlinked here in blue, so you can click on those if you're curious. Mark's question is actually a model that I think is kind of a hybrid of the two papers here. So in this paper up top, I'll just call it this land economics paper, we applied this method in the Grand Canyon to conservation of endangered humpback chub, where the management intervention was electrofishing of predatory non-native trout that prey upon the chub that they're trying to conserve there. So in that context, we used it to think about, how, not in a fisheries exploitation context, but in I think a context that's at least partly similar to what Mark was thinking of, in that this is a species that's already in trouble and we're trying to help it, trying to come up with an intelligent way to think about how aggressively you need to electrofish depending on how many trout you have and how many chub you have in your population assessment. What doesn't match up in that paper with Mark's question is in that land economics paper, it's the US Geological Survey that's going out and doing these electrofishing trips. So it's still centralized management. But the framework that we laid out here, it's fairly straightforward to identify, say, a price per unit of some effort that then you could pay individuals in order to achieve this in a decentralized way. Of course, the stark difficulty there is enforcement. So I glossed over that. We didn't really spend too much time on that, but we assume in this system that you've got observers on board that can see when turtles are being caught as bycatch and therefore enforce this bycatch price. And that's a feature of the real world. There are observers on boats, but there's a cost to that, and it's not a problem-free system. So anytime we talk about achieving this through a decentralized approach, the model in this paper can definitely, or I don't know, that's maybe overconfident, but could almost certainly be used to identify the price instrument that you might want to use, or how to set that. But probably the larger question would be, is it can you think, is it reasonable to expect that there would be a mechanism for enforcing that and having those payouts be for the behavior that you want?
Cool. So we have one final question, and we have lots of people that have given you kudos in the questions as well. But the final question is from Kelly Andrews, and Kelly said, have you applied this using the EcoCast model to answer how much you might increase profits if fishermen perfectly use that model to decide where to fish? And how would you include the error in the EcoCast model in addition to your X-min value and delta value?
Gotcha. Okay, so I think I think I heard it right that this was a question about EcoCast, and so that this was just to remind folks, this was coming from a separate analysis by others. This wasn't work that we did. We just sort of took advantage of this as a nice, interesting visual to set up the scene. They identify here along the California coast, at least, areas that are either better or worse for bycatch of leatherbacks. And so the question here is, have we valued in this model what would be the value of fishermen being able to take advantage of this spatial information here? And the answer to that is no, because we didn't consider spatial choice of the fishermen as one of the margins of adjustment. Now that's clearly an important margin of adjustment. And so I think that's definitely an important question. We did value what would be achieved if you were to jump from an MPA style regulation to the effort-based approach, and I glossed over that, but under the assumptions of the model here, we estimate that swordfish revenues, net revenues, could go up by about $4 million a year, or 5 times greater than under current management within the MPA. So that's a rough estimate. Our model didn't incorporate all elements of reality. Importantly, all the different margins of adjustment that fishermen might take, like spatial choice, gear choice, time of day, and all sorts of other things. So we didn't incorporate all of that. So, I would take this number with a grain of salt, but it suggests, we could, by increasing flexibility while still achieving the viability goal, we could have a much more profitable fishery.
All right, so that was our final question for the day. Thank you everyone for joining us and asking great questions. And thanks again to our speaker for presenting as well. Yeah, so thank you again, and for everyone staying tuned, we'll see you all next week for our seminar again. Thanks again.